approximate method of analysis. Approximate method is required because if you see, we have seen so many methods of structural analysis, slope deflection method, Carriage method, moment distribution method, and so on. These methods require so much of time because if number of degree of redundancy increases, then those many numbers of unknowns are required to be solved, which is very tedious. That's why people develop this method called as approximate method of analysis, which is for two cases. One is for gravity load and also for lateral load. Now in gravity load we have dead load, then we have live load which act vertically downward, and in lateral we have wind, seismic forces, or any other force which is acting in the lateral direction. Now first of all let's discuss the gravity method, which is fairly simple. If you understand few basic things, then you will be able to solve any number of bays, any number of building frames, which is very simple. Just understand first what is the bending moment diagram for the simply supported beam subjected to certain UDL load entire span, which is, let's say, W kN per meter and the span is L. Now if you draw bending moment diagram for this value is at mid span, which comes out to be WL squared by 8, and the bending moment is 0 at the support. Now if you see, there is a point of 0 bending moment which is lying at both the ends. Right? Similarly, if I change the support condition over here, instead of making it hinged, I make it fixed. Now the same beam with same span is now a fixed beam. Now you have studied already, the beam has two bending moments which are positive as well as negative. The value of bending moment at mid span is WL squared by 24, here it is WL squared by 12, which is negative. This bending moment is totally sagging, which is positive in nature. These bending moments are negative and this mid span bending moment is positive, because the beam bends something like this. Now this distance or point of inflection is normally at a distance of 0.21 L from the support. Point of inflection is nothing but point of zero bending moment. Now in reality, building frames, if you see, this is a building frame, typical 2D building frame, subjected to certain amount of load. Now if you check the support conditions, they are neither fixed nor completely fixed nor completely simply supported. So to get a value of point of inflection, it is basically based on the experience of the engineer where he wants to put the point of inflection. In other words, it is directly calculated as 0.2 plus 0.21 L divided by 2, which is nothing but 0.1 L. So it is the assumption that it says point of inflection or point of zero bending moment will be at a distance 0.1 L from the supports. Now if you check a typical fixed beam, what is the degree of indeterminacy of this? This DSI becomes 0 and DSC becomes R minus 3, which is nothing but 3. Therefore DS becomes 3. To make the structure determinant, we have to have three assumptions so that we can simplify, or we need to develop three additional equations which can help us to solve three other unknowns. To simplify this building frame analysis, we make such assumptions that every beam will have point of inflection at 0.1 L from the support, and these are the two hinges that will give you two unknowns. Plus one more assumption we make is that axial forces in the beam is taken as 0. And for that we have separate method of analysis. Combination of the two will be your final bending moment. So for now we have three assumptions, which are those. If you check, degree of static indeterminacy is 3. So to simplify that, we have point of inflection acting at a distance 0.1 L from each support. Okay, so let's start and analyze this building frame, which is having 3 bays and it is subjected to 30 kilonewton per meter load on each floor. How many floors we have? 1, 2, 3 and 4. So I have first floor, second floor, third floor and the top floor is 4th floor. Now if I wish to analyze any floor, I will simply take one beam at a time. Let's name this as ABB for instance, and rather make it ABCD. So if I take AB here, the span of the beam is now 4 meters and subjected to a UDL of 30 kilonewton per meter. Now if you check, I will divide this beam in 2 separate parts such that I have point of inflection which is going to be 0.1 L, which is nothing but 0.4 meter from either side. So what is remaining in between is 3.2 meters, right? Now I will draw free body diagram so that you can understand this better. I will divide this beam as subjected to UDL of 30 kilonewton per meter over a span of 3.2 meter, and the same beam will have 2 cantilever projections which are nothing but this, which is 0.4, and this is 30 kilonewton per meter. This is also 30 kilonewton per meter. This is also 30 kilonewton per meter. Now if you check what is the total load out of this, 30 into 3.2, what is the value? It is 30 into 3.2. Now if you check, this total load is going to be 30 into 3.2, which is nothing but 96 kilonewton. So this separate simply supported beam, which is having a span of 3.2 meters, will have reaction of 48 kilonewton each. Now this reaction is going to act as a point load on the remaining portion of the beam, which is nothing but, and it will act in the opposite direction because you have assumed a hinge or point of inflection here, which is nothing but 0.1 L from support. Now if you check 48 kilonewton, the span is total 0.4 meter. Now this load is 30 kilonewton per meter. Now you can easily calculate the bending moments. What is the bending moment here? You already know, for a simply supported beam with UDL over entire span, the maximum bending moment is nothing but WL square by 8. Okay, that value you will get directly. And bending moment at A, if you want to find, it is nothing but bending moment calculated at A, which will be, if I say this is A, so bending moment at A will be equal to 48 into 0.4 plus, rather if I take both moments as negative because they are hovering in nature, so this will be 30 into 0.4 into 0.4 by 2. Bending moment minus 48 into 0.4, which is this distance, then minus 30 into UDL moment, that is 30 into 0.4 into 0.4 by 2, that is nothing but 21.6 kilonewton meter at A. See, always if you remember, just look at this. Whenever we have beam will have a span moment and a support moment. So if I divide this in 3 parts, this is mid-span moment and there will be a end moment. In any continuous beam you already have studied, whenever we have a continuous beam, it will have a negative bending moment at support. So these values are nothing but the negative bending moments at supports, and span moments are sagging bending moments which are positive in nature, which will act at mid-span. So I got positive bending moment from where? This is WL square by 8 straight away. So it is nothing but 30 into 3.2, because we have excluded 0.4, which is nothing but 0.1 L, that is assumed point of inflection from support. So 4 meter is the total span, 0.1 of that is nothing but 0.4. So 0.4 on either side, whatever is remaining is 3.2. So this portion is assumed to be acting as a simply supported case. So bending moment is WL square by 8. That bending moment we already know, that is nothing but what is the bending moment? Just a second, I will tell you. The bending moment is 38.4 kilonewton meter. Okay, so mid span moment here is 38.4 kilonewton meter. So if I analyze only one level, or you can say one story, bending moments for beams are repetitive, even for the columns are the same, right? So we will just see beam BC now. If you check beam BC has span of 6 meter. Now again I will have to get points of inflection, which are nothing but the points of zero bending moment, which is assumed to be acting at 0.1 L from the support, which is the assumption. So if I take 6 meter, 0.1 of that is 0.6. Now 0.6 from either end, so it remains at 4.8, 6 minus 0.6. So I have a simply supported span of 4.8 meter. So if I take span moment, which is nothing but acting at the mid span, which is static in nature, is 30 into 4.8 square by 8, WL square by 8, which is nothing but 86.4 kilonewton meter, which is positive in nature. Now if I wish to calculate bending moment at, let's say, B and at C, this is nothing but regular calculation. Now if you check 30 and 4.8 is the span, reaction of this is 72 kilonewton. Now as we have assumed the point of inflection acting at 0.1 L, direction of forces will reverse on the other side. So if 72 is acting at upward direction, so on other hand, or other side of the point of inflection, 72 kilonewton for balancing, because summation of vertical forces at this point has to be 0, it will act in the downward direction. So this same 72 acts as a point load at end of this cantilever B, which is nothing but extension of the BCB. Now I will have to calculate moment at B, which is nothing but end moment at B, which will be just straight away calculation minus 72 into 0.6 minus 30 into 0.6 into 0.6 by 2, which is nothing but 48.6 kilonewton meter, which is also negative, that is humming bending moment. Similarly, if you take this third bay, which is nothing but 5 meters long CD portion, now again I have CD portion 0.5 meters, so 0.1 L of that becomes 0.5. Whatever is remaining is 4 meters. So straight away mid span moment will be 30 into 4 square by 8, which is the standard formula you all remember, which is nothing but 60 kilonewton meter. Now if I have to calculate bending moment at C, okay, so I will get that as cantilever bending moment. So moment at C, if you check, it will be 60 into minus 60 into 0.5 minus 30 into 0.5 into 0.5 by 2, which is nothing but 33.75 kilonewton, which is again humming in nature. Now if you check, I can easily draw bending moment diagram anywhere. The beam bending moment diagrams for all the beams are the same. I will simply draw it here for our reference. I will draw negative bending moments at top and positive bending moments at bottom. Now if I check end moment at A is how much? If you check, it is 21.6. But the same bending moment at B, if I check from AB span, the bending moment is 21.6, and from BC span, if you check, the bending moment is 48.6. That means the joint is not balanced. Okay, that cannot happen. Then what is the other member who can bring equilibrium in the system? That is nothing but the column. So whatever is the unbalanced moment out of these two will be sent to column. So column will take whatever is the remaining. For instance, I will do the calculation for you. See, 21.6 is coming from AB span and BC span is having 48.6. So difference between the two is how much? I will directly calculate. This 48.6 minus 21.6. So the difference is 27 kilonewton meter. This difference will be taken up by the column. Similarly, if I go to joint C, if you compare again, I am getting 48.6 kilonewton meter bending moment at C. Okay, here if we check again, if I take moment at C, it is going to be the same. Okay, it is nothing but 72 into 0.6, that is minus, then 30 into 0.6 into 0.6 by 2 from BC span, which is nothing but 48.6, which is hogging the nature. Similarly, I have a bending moment of 33.75, which is coming from span CD. Again, the joint is not balanced. So, whatever is the difference between the beam moments at the joint is distributed to column. Okay, so I can calculate that as well. What is the value, for instance, if we take the difference here, I will just write in this portion the value from, always do the calculation like whatever is the difference that is to be distributed. So we'll subtract greater from smaller. So moment transfer to column will be 48.6, which is coming from BC span, and CD span is having 33.75. So this much bending moment is transferred to column. So the difference is 40.85. This much bending moment is transferred to column. So let's draw bending moment diagram. I will draw here first for the beams, then I will draw it for columns, which are repetitive for all floors. For gravity loads, bending moments in beam and column will be the same. So here I have end moment, which is nothing but 21.6, so I will plot it here. Then I have 48.6, I will plot somewhere here, it is 48.6. Then we have end moment, which is 33.75. So bending moment in BC span, always we will take the greater value at joint, because see, this is approximate method of analysis, and we always design for worst combination of forces or worst values of the forces. So those bending moment at C, we have two values, which is 48.6 and 33.75. We will take the greater of the two. For BC span, no doubt for CD span we have only one bending moment, which is nothing but 33.75. So this bending moment diagram. Now midspan bending moments also we know. The midspan bending moment for AB beam is, midspan bending moment for AB beam is 38.4. So I will draw it like this. This is nothing but 38.4, which is acting at midspan. Then we have BC member. So BC member midspan bending moment is 86 point something, so it is 86.4. So we'll draw it like this. This bending moment is 86.4. Now for CDB we have 33.3 bending moment acting here. We'll take this as 33.75 at the end, and the bending moment at midspan is 60 kilonewton. So this is comparatively lesser bending. These are the positive bending moments. These are the negative bending moments for which we have to design our beams. Now these are the bending moments for the beam. Here you can have 33.75, which is for this beam. Now difference at the joint. Now here if you see what is the difference at the joint, it is 21.6 straight away. So I can draw bending moment for columns also, which is nothing but 21.6, 21.6. This is the bending moment taken by the column. Now for joint B, what is the difference? Just now we have calculated the difference is 48.6, which is from BC, and 21.6 is the end moment from AB span. So that bending moment is 27. So that bending moment will be taken by the column. So 27 and then 27 kilonewton here also. Then if I go to joint C, what is the difference between the moments? It is 48.6 minus 33.75, which comes out to be 14.85. So we will have 14.85 in the column here. And the last, again I have 33.75, which is nothing but the unbalanced moment. Straight away goes to column, which is nothing but 33.75 kilonewton. This way you can draw bending moment diagram for beam as well as column for gravity loading. Nowadays we always use sophisticated computer programs like ETAP, SAP, maybe StatPro, but we have to analyze a 2D frame so that we get confidence in the use of the software. These values may not match exactly with the software, but they will be some very close to the software values, because unless and until we understand what is the logic behind this program, you cannot utilize or understand the basics of the software, and you cannot solve the complicated problem. These are very straightforward and simple methods. So for gravity load, just understand one simple thing. Beam is divided in two separate parts. One is the cantilever portion, which is nothing but 0.1 L from the support, and then the central part, which is the simply supported case, nothing but whatever is the remaining span. So combination of these two is the bending moment. Whatever is the balance, that is distributed to column. It is as simple as that. You can easily solve the problem. Best wishes. Thank you.